Okay, so in this section, this is 8.4. What we're going to do is we're going to look at a phenomenon called half-life. It's a property of radioactivity. So let me bring up a screen here, a little outline here. So we're going to look at half-life. This is section 8.4. The half-life is the amount of time that it takes for a material to decay to 1/2 its original amount. So if you recall from the previous section, we said that some materials are radioactive, they're unstable, and their nuclei will break apart or emit particles in order to become more stable. The idea is that unstable things eventually become more stable by changing into something else, okay? So uranium becomes more stable by converting into, say, thorium. So the amount of time it takes for half of the material to undergo radioactivity is called the half-life. So half-life will have the units of time. So it could be in seconds, it could be in minutes, it could be in hours, it could be in years. Depends on the material. Here's a few examples. Carbon-11, which we'll look at an example of. This is used in PET scans. Carbon-11 has a half-life of a little more than 20 minutes. When we do our calculations, we'll just put it as 20 minutes. It's a little bit more than 20 minutes. Radium-226, which is a fairly dangerous material because it comes from radon, has a half-life of 1,600 years. Carbon-14 has a half-life of 5,730 years, and then potassium-40 has a very long half-life, 1.3 billion years, okay? So let's look at the example of carbon-11. So let's say we start with a clock. We'll put the clock right at 12 o'clock. Okay, it's noon time. And we have 16 micrograms of carbon-11. So that's the mass of carbon-11. The half-life is 20 minutes. We already know that. So what that means is after 20 minutes, you should have half as much material. So half of 16 would be 8. We'd have 8 micrograms. So after 20 minutes, so now it's 12:20, we should have half as much. So that would be 8 micrograms, right? Half of 16 is 8. Okay, let me just actually write this down here. 1/2 times the amount you start with, 16, that would be 8. So we'd have 8 micrograms left. Okay. So now let's go another 20 minutes. So now we're at 12:20. We're going to go another 20 minutes. So we're going to go till 12:40. Well, after that, by 12:40, we should have, again, half as much. So 1/2 times 8 micrograms should give us 4 micrograms, okay? So that'll be 4. So that, now we're at 12:40, we have 4 micrograms. Now let's go another 20 minutes. Another 20 minutes will get us right to 1 o'clock. So 1 o'clock, so we go 1/2 again. So if we have 4, 1/2 4, that should give us 2 micrograms remaining. So at 1 o'clock, we should be down to 2 micrograms. Let's go one more. Let's go to 12:20, another 20 minutes. So another 20, we're gonna go half as much, right? Sorry about that. So 1/2 times 2, we should get 1 microgram. And that's what we'll have. At 1:20, we'll have 1 microgram left. So every 20 minutes, you go down by half, okay? So there's different calculations you could do. I could give you the amount of time, and then you could figure out how much is left. But notice we're doing multiples of the half-life, okay? So this method does not allow us to do fractions of the half-life. So we couldn't do 25 minutes or 15 minutes. It has to be multiples of the time. If we were doing the same problem with carbon-14, it would be multiples of 5,730 years, okay? Now, let me show you the data that we have here, and I'm going to extend it a little bit. We didn't show you this on the clock. But if we go up every 20 minutes and then just take our mass, 16, 8, 4, 2, 1. Remember, it's turning into something else. It's not disappearing. So if you've lost 8 micrograms, that's because it turned into something else. And I went ahead and calculated it all the way out to 160 minutes. So a little bit under 3 hours. That's 2 hours and 40 minutes. Take a look at what we go. It gets smaller and smaller and smaller. But notice it doesn't really get to zero. You could go out as far as you want, and it'll get smaller and smaller and smaller, but it never actually gets to zero. Okay. So here's a graphical analysis. This is going to show the same data. So I just took all these numbers here and I put it in a graph. So this is the carbon-11 decay over time. On the y-axis, the vertical axis, I have the amount that's remaining in micrograms. And then on the x-axis, I have the amount of time in minutes. So this graph corresponds to this data. So at time equals 0, we should have 16 micrograms. At time equals 20 minutes, we should have 8 micrograms. So let's see what happens. 16 after 20 minutes, which is right about here, we have 8. After another 20 minutes, which is 40, we're down to 4. After another 20 minutes, which would be 60, we're down to 2. After another 20 minutes, which would be down to 80, we're down to 1. And then 100.5, 0.125, and so forth and so on. So it's approaching 0, but it never really gets there. Okay. So that's called half-life. And it's important because if we're dealing with radioactive materials, for example, carbon-11, if your patient has been injected with carbon-11, he's radioactive. And so we may not want to send them out into, into the streets until that carbon-11 is decayed away. So we want to use a radioisotope that decays away rather quickly. So it's gone after a little while, right? So carbon-11, by the time you're down to about 2 hours, so that would be 120 minutes, okay? You've only got about 0.25 micrograms left. There's very little of it, right? So that's 120 minutes is right here, about 0.25 micrograms. It's almost all gone, there's very little bit of it left. You want to be on the safe side and go to like 3 hours, that'd be 180 minutes. That would be down here about 180 minutes. And that, yeah, right there, there'd be, very little of it left. It would be relatively safe. Okay. So let me show you one problem here that's given in the textbook to kind of think about this. So I'm going to look at example 8.3. Okay. So here it says that potassium 40, which is K1940, decays into argon 40, okay, with a half-life of 1.3 billion years. Okay, so now let's say we have a rock. Okay, and there's no argon 40 present. Okay, as potassium 40 gradually decays into argon 40. Okay. The argon gets trapped in the rock as a gas. Can't escape. Okay. Comparing the amounts of potassium 40 and argon 40 okay, in the rock allows us to determine the age of the rock. This is actually one of the ways we determine how old rocks are. Okay. How old is the rock if it contains 3 times as much argon 40 as potassium 40. Okay, that's really, after all that intro, that's the idea. That's the question. So again, yeah, this rock, argon is a gas. So what happens is if you have a rock and it's really hard, so it's like molten, like lava, it's not going to have any argon in it because it's too hot. The gases will escape. But as it cools, the potassium 40 is going to turn into argon 40. Okay. So the longer it's sitting around, the more argon you're going to have and the less potassium. Okay. So if it's been sitting around for a long time, like billions and billions and billions of years, you're going to have a lot more argon than you have potassium because the potassium is being converted into argon. So let's do it this way. Let's suppose I'm going to write a little table. Okay, so let's say this rock is new, it's fresh. Right, came from a volcanic explosion, lava came out, it starts cooling. At the beginning, we're going to have some potassium 40. So I'm going to start off, I'm just going to make up a number like 1. And this will be 0, right? Because when the rock is fresh, there's no argon because it's a gas. Potassium is a solid, but argon is a gas. So that gas will escape. There won't be any. But then let's go 1.3 billion years. Okay, BNY for billion years. This should go down by half, so it should be 0.5. And this should go up. So the amount that we lost, 0.5, should be the amount that we gained. Okay, so after 1.3 billion years, we should have the same amount. The ratio should be 1 to 1. So let's do a little ratio. Argon to potassium. So here it's 0. There isn't any argon at the beginning, but now the ratio is 1. Okay. Now let's go another 1.3 billion years. So now our total would be 2.6 billion years. Well, this should go down to 0.25, right? Every half-life, it's going to go down by half. So you just take half. Okay. Now this went down by 0.25. So this is going to go up by 0.25 and it'll be 0.75. Okay. Now this ratio is 0.75 to 0.5. If you put that in your calculator, you get a ratio of 1.5. Okay. Let's go another 1.3. That would be now 3.9 billion years. Okay. This is going to go down another half. So just keep going to half. 1, 2, 5. So this one went down by 0.125. So this is going to go up by 0.125. So 0.875. Okay. Now let's do this. This would be 0.875. Okay. And this one would be 0.125. Okay. We now have a ratio, what is that? 2, 4. Actually, I have to do that in my calculator. Sorry. 875 divided by 125. Seven. Okay. So if you take a look at this ratio is 7. Okay. So it looks like after 2.6 billion years, oops, sorry, the ratio was 3, my mistake. 0.75 divided by 0.25. Stop. That gives you a ratio 3. Now 0.875 over 0.125. That would be equal to 7. So let's take a look at our ratios. When it's fresh, the ratio is 0. After 1 half-life, the ratio is 1. After 2 half-lives, the ratio is 3. After 3 half-lives, the ratio is 7. Okay, so it looks like our answer would be right here. That's when the ratio is 3, and that appears to have occurred at 2.6 billion years. Okay, so if that ratio is 3, that tells us that the age of this rock is 2.6 billion years. Okay, let me show you one more. I'm going to take a look at an end of chapter problem here. Okay. Okay. So this is number 40 at the end of the chapter. And it says, after 45 minutes, I'm sorry, 45 hours, I'll write out hours, 1 milligram of an 8 milligram sample of radioactive sodium. They don't tell you what kind it is, remains undecayed. Okay. The half-life of the isotope is, and we have a question mark, okay? So let's take a look at how we can analyze this. Okay. There's 1 milligram of the original sample remains. So this is what I'm going to do. The original sample has a mass of 8 milligrams. Okay, so let's do this. After 1 half-life, how much should we have remaining, right? We don't know the half-life, but let's just say after whatever it is, how much should we have? Again, the half-life is the amount of time it takes to go to half as much as you started off with. So half of 8 would be 4 milligrams. Okay. Let's do it after 2 half-lives. Okay. Well, after 2, it'd be half of what we have remaining. Half of 4 would be 2 milligrams. And let's keep going. After 3 half-lives, half of what we had. That's 1 milligram. Now we've reached a point where we have the amount that they said we had. We have 1 milligram remaining. So it looks like that was 3 half-lives, right? 8, 4, 2, 1. That's 3 half-lives. So we know 3 times the half-life. Okay. Gives us 1 milligram. Okay. So now what I'm going to do is I'm going to take the amount of time. The amount of time is 45 hours. Oops. Okay. Well, that's our total time. So the amount of time it took right here is 45 hours. So all we got to do is divide that by 3. 1 half-life, 2 half-lives, 3. So if we take our total time and we divide that by the number of half-lives, that's going to give us the half-life. Okay, so that'd be 45 hours over 3, and that would give us 15 hours. Okay, let's check that. Let's claim that the half-life is 15 hours. After 15 hours, we would have 4 milligrams. After another 15 hours, which would be a total of 30 hours, we would have 2 milligrams. And after another 15 hours, which would be a total of 45 hours, we would have 1 milligram. And that's exactly what they said. They said we started off with 8. After 45 hours, we had 1. Okay. So that does it for half-life.